In this video, we're going to look at how to calculate the moment of a force. So far, we've studied the equilibrium of particles and found that a particle is in equilibrium if the resultant force acting on the particle is zero. If we now consider a rigid body with two equal but opposite forces acting, then the resultant force is clearly zero, but the rigid body is going to rotate, so the object is certainly not in equilibrium. The forces have got a turning effect, and we've got to consider that turning effect. So, try and motivate the idea of the moment of a force. Consider a rod resting on a table, attached to the table by a smooth pin at the point O. Suppose a force F parallel to the surface of the table is applied. What we're going to look at is a short video that illustrates the possible motion of the rod. What does the rotation of the rod depend upon? So we're changing the magnitude of the force F at this stage. And we can see that the rotation is less. If we reduce it even more, the rotation is even smaller. For the next two or three animations, we're going to change the angle of the force F. Changing the angle of the force F has also slowed down the rotation that we've got. And for the next ones, we're going to change the position of the force F. And we can see that that again certainly changes the rotation that we get. So putting these results together, we can see that the amount of rotation and the direction of the rotation depends upon the magnitude of the force, the angle that the force makes with the rod, and also the point of application of the force. Now these observations together make it reasonable for us to define the turning effect or moment of a force about the point O as being the product of the force, or the magnitude of the force, and the perpendicular distance, d, of the line of action of the force from O. Strictly speaking, moment is a vector quantity. The direction of the moment is at right angles to both the force and the line joining O to the force. In practice, though, for the examples that we'll be looking at, a force that gives an anti-clockwise turning effect has a positive moment, and a force giving a clockwise turning effect has a negative moment. The unit of moment is the Newton meter, or which we abbreviate down to just Nm. The resultant of several moments is simply the sum of each of the individual moments. So, the diagram shows the view from above of a rectangular sheet of metal of length 10 meters and width 2 meters. We've got to calculate the moment of each of the forces about an axis through the point A, and we've got to find the resultant moment. The moment of the 5 Newton force is going to be equal to 5 times 4, and the 5 Newton force is trying to turn the sheet in an anti-clockwise direction. So we've got the moment of the 5 Newton force is 5 times 4 anti-clockwise, or 20 Newton meters. The moment of the 6 Newton force is 6 times by the distance, the perpendicular distance of its line of action away from A, and that perpendicular distance is 9 meters. It is also trying to turn the sheet in an anti-clockwise direction, so the moment is 6 times by 9 in an anti-clockwise direction, which means we've got a positive moment of 54 Newton meters. The moment of the 8 Newton force, well, the 8 Newton force is trying to turn the sheet of metal in a clockwise direction. So the moment is going to be 8 times 6 in a clockwise direction. But a clockwise moment is a negative moment, so that means we've got a moment of minus 48 Newton meters. The resultant moment is the sum of all of the moments we've got, so that is 20 plus 54 plus minus 48, which gives me a positive moment of 26 Newton meters, or if you like, 26 Newton meters in an anti-clockwise direction. For example 2, we've got the diagram shows another sheet of metal with 2 forces acting on it. We've got to calculate the moment of each force about an axis through A and find the resultant moment, and then we've got to do a similar thing for an axis through the point B. So, for part A, the moment of the 3 Newton force about A is 3 times by 0.6, but it's trying to turn the sheet of metal in a clockwise direction. So we've got a moment of 1.8 in a clockwise direction, which means that the moment is minus 1.8 Newton meters. The moment of the 5 Newton force about A, well, the 5 Newton force is also trying to turn the sheet of metal around in a clockwise direction, and its line of action is 1 meter away from the point A, so its moment is 5 times 1, which is 5 in a clockwise direction, giving a final moment of minus 5 Newton meters. The resultant moment about the point A is equal to minus 1.8 plus minus 5, which is minus 6.8 Newton meters. Now considering the moments of the forces about an axis through the point B, we have the moment of the 3 Newton force about the point B is 3 times by 0.4, which gives me 1.2 in a anti-clockwise direction. So that means I've got a moment of plus 1.2 Newton meters. And the moment of the 5 Newton force about B is 5 times 0, because the 5 Newton force actually acts through the point B. So that gives me no moment at all. So that gives me 0. And the resultant moment about B is 1.2 plus 0, which is 1.2 Newton meters. Now in example 3, we've got a square sheet of metal of side 1 meter, which is acted upon by 2 parallel forces with magnitude P newtons and Q newtons. We're told the resultant moment of the forces about the point A is minus 5.5 Newton meters, whilst the resultant moment of the forces about the point C is minus 1.5 Newton meters. So we've got to determine the values of P and Q. So, if we consider the moment of the force P about A, that is P times by 0.2 in an anti-clockwise direction, so that gives me a moment of positive 0.2 P. The moment of Q about A is Q times by 0.7 in a clockwise direction, so that gives me a moment of minus 0.7 Q. I know the resultant moment of the forces about A is minus 5.5 Newton meters, so that gives me minus 5.5 equals 0.2 P plus minus 0.7 Q. In other words, minus 5.5 equals 0.2p minus 0.7 Q. Now considering the moments about the point C, the moment of P about the point C is P times 0.8 in a clockwise direction. So that gives me a moment of minus 0.8p. The moment of Q about C is 0.3 times Q in an anti-clockwise direction. So that gives me a moment of 0.3 Q. We know that the resultant moment about C is minus 1.5 Newton meters. So I've got minus 1.5 equals minus 0.8p plus 0.3 Q. So I've got a pair of simultaneous equations for P and Q, which I can solve to obtain P is 5.4 newtons and Q is 9.4 newtons. Now at this stage I'd like you just to pause the video and to work out the resultant moment about the point O of the system of forces in each of the following diagrams. When you've done that, stop the video because the video is complete.